The problem states that the tow rope is pulling the skier up a hill, or sorry, a car that is going up a hill at a constant speed. So we're asked to draw the correct free body diagram. So the first step is to draw a dot for the object of interest. In this case, it is the car. Make sure not to draw a box or to draw a sketch of the object. And also make sure that we're going to check certain things before we draw any kind of vectors for the forces. So we're going to check if this is going up on a slanted surface, in which case it is. It's going up a hill. So we're just going to draw a slanted surface this way. If the problem doesn't ask you explicitly if it is going up on a hill, make sure to not draw axes because it just messes with things. It's not necessary. So then we are going to consider the first force that we always consider, which is weight force. All objects will have a weight force no matter the planet that it's described to be on, so weight force should be the first thing you consider. Another really important thing is to make sure that your weight force always goes straight down. If you want to make sure, just check against the straight edge of your paper, make sure it always goes straight down. And always make sure to label your forces. In this case, do not call it gravity because it's not gravity. So again, all of your vectors should connect with the object of interest, and it should always point away from the object of interest, not towards it. So then we want to assess if the object is resting on a surface, in which case it is. It's on a hill, the car is on the hill. So then we want to make sure that you are going to be drawing a normal force. Normal force will always exist as long as an object is on a surface, and it will always point out and perpendicular to the surface. So because we have a slanted surface, we're going to make sure our normal force is perpendicular to that. And that would kind of go in this direction. So you kind of have this like perpendicular action. Okay, and the length of the arrow in this case will always signify the magnitude. So you do want to make sure that these two lengths and these two lengths are approximately the same. And then we are going to be considering whether or not this problem is asking for a constant speed or if it's accelerating up a slope, being pulled. So because this object is moving at a constant speed, we have to make sure that all of our forces are actually balanced out. This may not be as manifest as you may think. What we're typically tempted to do is to draw the vector for, I forgot to label this, to draw the vector for the tension and also the friction to be the same length. However, if we do that, which would look like this, what we would have to consider is that even though we're not supposed to draw components on the free body diagram, we still have to consider it. So this would be weight y, the vertical component of the weight, and this would be weight x. So this weight x length is still exerting weight force in that direction. So if we're adding this onto here, weight x, this would make this entire length overly long, and hence it would not be at a constant speed, because make sure constant speed and the object at constant speed and the object at rest will always have a net force of 0. And in this case, it won't have a net force of 0. So if we make this a little bit shorter, well, still on the axes, you'll have the friction force be a little shorter, and then once you add this length onto here, it will balance out with this. So the correct free body diagram in this case, just to clean up all the edges, would be something that looks like, and you don't want the components here, would look like this.